Welcome to section 10.2. We're going to be using combinations and binomial theorem. Now you did permutations in section 10.1. We're going to relate the two together, and then we're going to show you how to then look at combinations in a different application. Okay? So take a look. Our job for a combination is to figure out number of ways an event can occur when, underline, bold it, star it, whatever you need, when the order matters. And this is huge for us, okay? And what that says to us is, I apologize, this shouldn't be when order does matter. This is when order does not matter. Basically, as you look, what that says is, and most of the time you see combinations when you look at a group. Things like, you know, I'm picking a committee instead of picking a president, vice president, things like that. And that's some of the stuff that we're going to kind of discuss in class. I want you to take a look at the combination formula that's there. Again, this can be put in your calculator under your math probability section, but I want you to know why things are different. Okay, so let's look at a couple examples. I want to pick 7 books from a stack of 32, and I truthfully don't care what order I pick the books. I just want 7 books, and that's what's different about a combination. So what I'm going to do is 32 combinations of 7. The way the formula works says take 32 factorial over 32 minus 7 factorial and 7 factorial. And this extra piece right here is trying to eliminate the duplicates. And so what I mean by that, let me tell you shorthand, is basically what I'm trying to say is 1, 2, 3 is the same thing as 2, 3, 1, which is the same thing as 3, 1, 2, which is the same thing as 3, 2, 1, which is the same thing as 2, 1, 3, and so on and forth, or 1, 3, 2. And I've looked at, there are 6 combinations. And what this says basically is I'm trying to say that all of these are going to be exactly the same. And so I don't want to count all 6 as different like I did with a permutation. In a combination, it says this is the same thing as one event with a 1, 2, and a 3 in it. And so that's what's different about a combination, and that's what this extra piece does. Now, we learned in combinations that you could take 32 times 31 times 30 times blah, 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 blah. 32 minus 5 is, or 7 is 25, and 24, and 23, and blah, blah, blah. And you can kind of do that there, and 7, and 6, and 5, and so on and so forth. Now, you can do that, or you can just let your calculator do the magic for you, and what you end up getting is 3,365,856. And we're going to kind of talk about that as we go through. But again, this extra piece here is important. Why is it there? Because all 3 of these need to be eliminated. All 6 of those need to be eliminated, and we count it as 1. Second idea is when to use a multiplication for our combinations and when to use addition. And again, it all comes back to our wording. And that's what's so important. When you talk about wanting 2 comedies and 3 family movies, and in mathematics means multiply. And so out of the 12 comedies I have, I wanted to pick 2. And out of the 9 family movies, I wanted to pick 3. So stick each of these in your calculator. And for 12, choose 2, you get 66. And for 9, choose 3, you get 84. I multiply these together, I get 5,544 different movie combos. I'm just going to shorthand this for a minute, but this is the idea. If you see the word and, you should be thinking about multiplying. If not, then you should be thinking add. And the words I'm looking for are at most, which means at most means I could have 0 movies, I could have 1 movie, or I could have 2 movies. Now the question is, how many total movies do I have to choose from? Well, if I go back up to my combination, up to the top, if I'm looking for total movies, I take 12 plus 8 plus 7 plus 5 plus 9, and you end up getting 41 movies. So I could, out of the 41, I could decide I don't really like any of them, so I'm not going to pick any. Or out of the 41, I could say to my kids, I'm sorry, you only get one movie for my 2 children. Or I could say out of the 41, each kid could pick one movie. Okay, and so that's kind of the idea. If I take 41, choose 0, I get 1, because there's only one way, you just didn't pick it. 41, choose 1, there are 41 different combinations of movies to look at. And 41, choose 2, there are 820. So if I add these 3 numbers together, you get 862. That's supposed to be a 2 movie combos. Okay, let's just do it this way. 862, so you know what I'm looking at. And so this is the idea. So if you're looking for an inequality, at least something like that, you're going to add the combinations together. If you see the word and, we're going to multiply. As I look here, your magazine has 11 articles. You want to read at least 2. Now, let's talk about that. What that means. That means I want to read 2, 3, 4, all the way up and say I want to read 11 articles. Now, we could add 11, choose 2, 11, choose 3, 11, choose 4, all the way up to 11, choose 11, which is fine, but I don't really want to do that. And so what I can do is kind of like the idea of a complement. I want to look at doing it the easier way. And I want to look at what's not being read. Now, you have 2 choices. You may either read it or not read it. Because you have 2 choices for each of the 11 articles, so if I look at my first article, I have 2 choices. My second article, I have 2 choices. All the way down to my 11th article, I have 2 choices. And what I do is multiply that together. So if I read it or don't read it, there are 2 to the 11th power, because I'm multiplying those 2 11 times, possibilities on how many ways to read it. Now, if I read at least 2 articles, then I didn't read 0 articles or 1 article. And so you're kind of looking at what's missing in the realm of the 0 to 11. So it's easier to do this. There are 2 to the 11th possibilities. And I can get rid of the possibility that I didn't read any of the 11 or that I only read 1 of the 11. Now, 2 to the 11th is 2048. 11 choose 0 is 1, and 11 choose 1 is 11. So 2048 minus 12 is 2036 ways. Okay, and again, we're going to talk about complement as it comes up later, but I wanted you to kind of see this idea. Is it quicker? If you want 11 choose 2, 11 choose 3, 11 choose 4, all the way up to 11 choose 11 is a possibility, or you can try and do it a little bit shorter way. If you don't quite understand the shorter way, shoot, add them up, okay? All right, we are also going to be working on something that we call Pascal's triangle. And Pascal's triangle is basically a way to relate combinations. Now, once you kind of see this, and maybe you've seen this before, it ends up being pretty nice. But here's kind of things to keep in mind, okay? And we're going to go kind of through this step by step. The first idea is every row starts and ends with a 1. Every other than 1, every other number besides 1 is the sum of the 2 rows above it. Okay, so let me explain what this means. We always start with a 0 row, which seems weird, but it does. And if I take 0 combinations of 0, and I stick it in my calculator, I get a 1. Then I go to the first row, and I always start with 0. I could do 1 combination of 0 or 1 combination of 1. And again, I'm going to stick these in my calculator. 1 combination of 0 is 1. 1 combination of 1 is 1. I do the same thing. I start with 0. In the second row, 2 combinations of 0, 2 combinations of 1, 2 combinations of 2. And what I think you're starting to see is that it starts at 0 and goes up to whatever row I'm working on. So 2 combinations of 0 is 1, and we said we start and end every row with a 1. Now the number in between that is the sum of the 2 terms above. 1 plus 1 makes 2. And so once you get yourself started, it's not too bad. Okay, so I start 3 combinations of 0, combination of 1, combination of 2, combination of 3. I start and I end with a 1, and the next term is the sum of the 2 above it. So 1 plus 2 is 3. And this term is the sum of the 2 above it. 2 plus 1 is 3. And so we're going to ask you things like, okay, what if I did the 4th row? I start with a 1, I end with a 1. I add the ones above it to get a 4. The ones above it, 3 plus 3 is 6. The ones above it, 1, 3 and 1 is 4. If I wanted the 5th row, I start and end with a 1, 5, 10, 10, 5, and then a 1. And so you can kind of see as you're going through, just know that when I get to the 5th row, I start 5 combinations of 0, 5 combinations of 1, 5 combinations of 2, 5 combinations of 3, combinations of 4, and I've got to end with 5 combinations of 5. So I start with 0, I end with the number that I'm on. So if you get that idea, let's talk about the 7th row. 7 combinations of 0, combinations of 1, combinations of 2, combinations of 3, 7 combinations of 4, 7 combinations of 5, 7, 6, and 7, 7. Now this is great, but it takes a lot of plugging in my calculator. There is a shortcut, and the shortcut you are going to want to use when we start doing more and more with combinations. If you go to your y equals menu, and you put 7 NCRX, and what this will do is allow us to look at our table. Now, when you look at your table, they give you the X and the Y. If you're looking at negative numbers, you will see errors because you can't take a combination of a negative number. But starting at 0, you're going to see 1, and at 1 is 7, and at 2 is something, and 3 is something, and it goes all the way down to 7, you'll see 1, and then 8, you'll again see 0. And so I want to look in this area right here. And what that will tell me are the values here in the rows of Pascal's triangle. So 1, 7, 21, 35, 35, 21, 7, and 1. And this is what you'll see in the y values if you use this idea. And please keep this in mind because, again, this is going to shorten our load later as we go through. So, similar idea. What's the 5th row of Pascal's triangle? And I'm going to simplify this a minute, and I want you to go to 5 combinations of x in your y equals, and let's find the 5th row. And we did it above, but 1, 5, 10, 10, 5, and 1. Okay? Now, let's talk about if I'm choosing 5 finalists, I have to choose 3 representatives. So I'm looking for 5, choose 3. Now, please remember that's the 4th value because I have to start with 0. So as I look at it, I start 5, choose 0, 5, choose 1, 5, choose 2, 5, choose 3. So the value is 10 combinations. Okay, so 5, choose 3 again is 10. And so just be careful because we're going to sometimes ask you about the 4th term. It's really 5, choose 3 because you had to start at 0. Okay, now, here's, I think, overall the kind of tough part. And I'm going to walk you through as easily as I can. But I would like you to be able to take a binomial, an x plus something, or I don't even care, 4x plus 12, and raise it to any power without actually having to FOIL. And that's our big thing. And I'm going to walk you through a couple of these. Your book gives you this ugly, ugly, ugly mess. Now, I'm going to show you the basic idea. I'm going to start, and I want to be able to look and figure out what each term kind of looks like. Okay? Now it starts the combination, and I multiply it by a to the r, b to the n minus r. And oh my gosh, this is so ugly. Okay, here's what your book says. Great, look at it, see how it works. Now let's move on. I'm going to give you this equation. Okay? This exponent above tells us that we need to look at the third row in Pascal's triangle. And so we're going to stick y equals 3 NCRX into our calculator and get the third row. Now remember, the third row are combinations, which is why it starts out NCR, combinations. Now when I go to the third row, I know that the third row of Pascal's triangle looks like this. 1, 3, 3, 1. You will notice I left significant space between them. I do this in a 3-step process, and I want to walk you through that. So I start with the third row of Pascal's triangle. Those are my coefficients. I then look at my x, okay? And I'm going to start at the third and work my way down. So I multiply by x cubed, I multiply by x squared, x to the first, and then multiply by x to the 0. And you'll notice I started 3, 2, 1, 0. If I had the fifth row, I'd go 5, 4, 3, 2, 1, 0. With the 4, I'm going to work backwards. So this time I'm going to say 4 to the 0 power, 4 to the first, 4 to the second, 4 to the third, and I'm going to add these values between. Okay, let's talk about, once you do that, it is all down to simplification. Okay, so here's how it works. Anything to the 0 power is 1, so I'm going to cancel those off because I really just don't even want to look at them and make it confusing. Okay, second step. 1 times x cubed is x cubed. 3 times 4 to the first. Well, 4 to the first is 4, times 3 is 12 with an x squared. I put a plus sign between them. 4 squared is 16. 16 times 3 is 48, and I have an x to the first. I'm just going to write x. 4 cubed is 64. 64 times 1 is 64. I put a plus sign between them. This is exactly what you'd get if you did x plus 4 times x plus 4 times x plus 4. And I just did it way quicker with you than it ever would have been if we FOILed it out. What I also love about this is I don't ever have to add like terms because there will never be any like terms. This binomial expansion eliminates so many mathematical errors. Okay, so keep in mind, this is kind of a weird look, but it is well worth it. Let me show you another example that gets a little harder. I have 2m minus n, and we never want to see a minus. So I'm going to call this negative n so that I can let my exponent rules do the work. Now let's go here. What row are we looking at? Fourth row. So I go y equals 4 NCRX, and I go to my table again, and I look at my table. My coefficients are 1, 4, 6, 4, 1. And again, I always start with my combinations first. Then I take the first value and I raise it to the 4th power. Because there's more than one item, you're going to put it in parentheses to multiply. 2m to the 4th, 2m cubed, 2m squared, 2m to the first, 2m to the 0. Then I take my negative n, which is my last term, and I start at 0. So negative n to the 0, negative n to the 1, negative n squared, negative n cubed, negative n to the 4th. Now, I'm going to do one step further than I did last time because I have extra stuff there. So I'm going to cancel out my zeros first because, again, if I can eliminate anything possible, I'm going to do that to start. Okay, exponent rule says you take 2 to the 4th and m to the 4th. Well, 2 to the 4th is 16, and I have an m to the 4th. I have a 4, 2 cubed is 8, and then I've got an m cubed. And anything to the first power is exactly what it is, negative n. I've got a 6, 2 squared is 4 with an m squared. And anytime I square a negative, it turns positive, so I have a positive n squared. I've got 4 times 2m. Negative n cubed is a negative n cubed. And last but not least, when you raise a negative to an even power, it turns positive, so I have an n to the 4th. now I'm going to write my answer. 16m to the 4th. I take 4 times 8 times -1 and get -32, m cubed with an n. Now, if you wanted to say minus instead of plus a negative, that's fine. 6 times 4 is 24. I have an m squared and an n squared. 4 times 2 is 8 times -1 is -8 mn cubed. Last one, n to the 4th. And once you simplify this, you have again easily foiled this out without actually foiling it out. And so we're going to practice in class tomorrow the binomial expansion, but I'm telling you guys, it is worth learning this to save yourself the headache and mathematical errors of FOIL. Last idea. The last thing says, I don't want you to FOIL the whole thing out. I just want to know what the x to the 5th term would look like. And the reason I don't want you to FOIL it out is we're talking, oh my gosh, the 9th row of Pascal's triangle, which is huge. Now I still need to know the 9th row. Okay, so I'm still going to have to look at this, but I want to talk about it. If I want an x to the 5th, what I'm going to do is look at 2x to the 5th so that I get an x to the 5th in my answer. Now, I'm looking at the -7, and because this was to the 5th, they've got to add up to 9. This is to the 4th. And this number back here always matched our combination, so I'm going to choose 9, choose 4. And so this is what I want you to keep in mind. They're giving you the coefficient or the exponent for your x. These two numbers will always equal up to the row of Pascal's triangle, and the back exponent is always the same thing as the combination we use. So I'm going to put in my calculator 9C4 using my math button. You get 126. I take 2 to the 5th, then x to the 5th, and I get 32x to the 5th. And -7 to the 4th is a positive 2,401. So my term looks like this. When I multiply 2401 times 32 times 126, I get 9,680,832x to the 5th. Now they don't want the term, they want the coefficient, which means the number in front. Here is my coefficient. Okay? Now this is one of the harder parts, is figuring out just one single term, and I promise you I'll give you more of those in class as well. But this is the end of section 10.2. And the big idea that I want you to come from is how to determine a difference between a combination and a permutation. We'll practice a bit of that in class. And also how to be able to expand using the binomial expansion. So that's it for 10.2.